Now that we can use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution, we can apply that to a change in pH that happens when you add strong acid or strong base to your buffer. The worst part of all of this is writing the equation. If you can write the initial equation, the rest of the math, that's fine. Okay, so let's say I want to calculate the change in pH that occurs when 0.01 moles of solid sodium hydroxide, strong base, is added to 1 liter of the buffered solution described above. So we're going to look at that acetic acid buffer, 0.5 molar acetic acid and 0.5 molar sodium acetate. Okay, well, for sure the sodium hydroxide is being added to the buffer, so it's going to be on the reactant side. Now, often these equations are written as net ionic, and in that case, I don't care about the sodium from either of these solutions. So I'm adding hydroxide to my buffer. Well, then I have to say, of the two particles in the buffer, the hydroxide reacts with which? There's got to be an acid and a base that react together in a buffered solution. And so if I'm adding base, it's going to react with the particle in the buffer that's acidic. That's going to be my weak acid, the acetic acid molecule. So first I got to get the equation. C2H3O2, that's my weak acid. It's going to react with the hydroxide. The definition of the acid is the hydrogen donor. So we're going to lose a hydrogen, give it to the hydroxide, and hopefully neutralize that hydroxide. We'll turn it into water. On the product side, I'll have the acetate ion and the water. All right, so guess what? The first part of this I often refer to as the buffer stoichiometry, or the BS. And it's going to come at you in the form of ice table. Gosh, we can never escape ice tables. They're so great. We can use them in so many different ways. We're going to set up an ice table with these guys. Okay, so now I look at what I have. Here's maybe something that's a little bit different between buffers and just a pure solution of a weak acid or a weak base. I've got a lot of initial numbers. So initially, the concentration of the acid is 0.5 molar. We're adding 0.01 moles of solid sodium hydroxide to a liter of this solution. So it'll be 0.01 moles per liter. And on the product side, I also know the concentration of the acetate ion. It's 0.5. But I don't care about the water. So kind of like with weak acids and weak bases, yeah, water is produced. It's very important. I mean, we're neutralizing the hydroxide, but I'm just not going to use it in any of my calculations. So I'll kind of scratch it out of my ice table. Wow, okay, does that kind of make sense? That the 0.5 molars, those come from the concentrations of the acid and the conjugate base that were given to you in your buffer. And then we're adding 0.01 moles of hydroxide to a liter of solution. Now you might be a little concerned here because we had said earlier, you know, you got to shift in the direction of the zero. Well, if you don't have any initial zeros, you have to calculate Q. Yeah, sometimes, but in this case, we won't need to. This just becomes a little stoichiometry, buffer stoichiometry, the BS. It's kind of just limiting excess. Then I look at my two reactants, and I find whichever one is smaller, and in a sense, that's going to become my limiting reactant. Well, I want the limiting reactant to be like the hydrogen or hydroxide that's being added to the buffer. I want the buffer to be in excess, because then I know that I have enough weak acid to donate hydrogen and neutralize all that hydroxide. Ah, okay, cool. So you're going to find whichever one's smaller, hopefully the hydroxide or hydrogen, and that's going to become our change. We're going to bring that down to 0. Oopsies, hello. We're going to bring it down to 0. I can subtract 0. I mean, just like any limiting reactant, the limiting reactant should be completely consumed. It's gone. Same thing here in my buffer stoichiometry. Bring that guy down to 0. And now that's your shift. That's your shift. This is a 1-to-1 ratio across the board. So my acetic acid is also going to go down by 0.01. So this is going to be 0.49 molar. And then on the product side, we're going up 0.01. So this will be 0.51 molar. And again, I don't care about the water. So a few fantastic things that come out of this. Yeah, we want to get rid of the hydroxide. Are there times when buffers fail? Absolutely. If I add more hydroxide than what I have in acid, like if I added 0.6 moles of sodium hydroxide, my buffer is a fail. Because now the limiting reactant would end up being the weak acid. If I added 0.6 moles of hydroxide, I would have 0.1 moles of extra hydroxide. And then I would still see a pretty significant change in pH. So yeah, we call it buffer capacity. It's a measure of like how much hydrogen or hydroxide can this buffer neutralize. Well, I can't go beyond 0.5 molar. And so yeah, we want to bring the hydrogen or hydroxide down to 0. It's gone. The other thing that we kind of mentioned early on is that, is there a change in pH? Absolutely. We're going to be losing a little bit of my original weak acid, and I'm forming a little bit extra conjugate base. But that conjugate base, the acetate ion, that's a weak base. I'll take that all day long in exchange for getting rid of the hydroxide. Again, if my goal is to keep the pH steady. So now once we do this buffer stoichiometry, which that's not all that bad, right? Now I still have a buffer. I still have a buffer. And that I still have the weak acid and I still have the conjugate base. It's just that I have to do this little ice table to figure out what the new concentrations are. But all I gotta do now is plug it into the Henderson-Hasselbalch equation. pH equals opposite log of the Ka, or pKa, which they gave us back in this earlier question. The Ka was 1.8 times 10 to the negative fifth. That'll be the same. 10 to the negative fifth plus the log of this ratio. It's always charged over neutral. So the charged ion is 0.51 molar acetate ion all over 0.49 molar weak acid. C2H3O2. So did you see what happened? My ratio changed a little bit. And yeah, my ratio is now like tipping toward the base, the negative conjugate base. So I'm expecting my pH to go a little bit higher, but hopefully not by much. So we just plug it all in. pH equals opposite log of 1.8 times 10 to the negative fifth plus the log of this ratio, 0.51 over 0.49. Got it. Okay, so I'm looking at about, I'm going to leave it an extra sig fig. I'm going to say like 4.76. Here's my new pH. Check this out. Okay, so when we did this question earlier, I only left 2 sig figs just because only 2 were given in the original data. But if I plug this in again, opposite log, 1.8 times 10 to the negative fifth, and if I were to leave a little bit more precision, I could say about 4.74. What a fantastic buffer. So if the original pH was 4.74 when it was a 1-to-1 ratio, yeah, my buffer changed concentrations a little bit, but the pH is 4.76. My pH only changed by what, like 2/100ths of a pH unit? That's fantastic. The more you can keep this ratio closer to the initial ratio, the less the pH is going to change. That is the beauty of a buffer, is that, yep, we're just going to shift this ratio a little bit. I formed a little bit more of the weak base. I reacted a little bit of my acid, but it had a pretty insignificant impact on my pH. Now, it does make sense that it went up just a little bit. The original was 4.74. This went up a little bit because, yeah, I've got a little bit more of the basic particle in the buffer. But compare this to what would happen if you threw that 0.01 moles of sodium hydroxide in a liter of water, which then would have just given you a 0.01 molar sodium hydroxide solution. Well, it would be a strong base, so right away we could just say POH is opposite log of 0.01 molar hydroxide. It's going to dissociate 100%. And I'm going to get a POH of 2, which then if I subtract from 14, I would get a pH of 12. Isn't this nuts? That the pH of the water, assuming that the water maybe started at neutral pH 7, that's a pretty significant change. It would have gone from a 7 to a 12. But not with my buffer. With my buffer, I went from a 4.74 to a 4.76.